This question is about intermediates in reaction mechanisms. Figure 3 shows an intermediate formed in the first step of a nucleophilic addition-elimination mechanism. Complete Figure 3 to show the structures of the two reactant species with curly arrows and relevant lone pairs involved in the formation of the intermediate. Draw curly arrows and relevant lone pairs on the intermediate to show how the final products are formed. So we've been given some clues. We've been told it's nucleophilic addition elimination, which we know happens to acyl chlorides. So I'm going to do some highlighting, and you wouldn't be able to do this in the exam, but it's just to show you what I'm doing. So we need to find the part of our structure that looks like the acyl chloride. So here is the C. This would have had the double bond O, and then the Cl would have been here. So that's one of our structures, which means if we want to look at our other structure, we need this methanol. So we've got a CH3, CH2, C, double bond O, Cl, and we've got a CH3, OH with a lone pair that's involved in the mechanism. So what happens is this lone pair attacks the delta plus carbon and opens up the double bond. That is how it became an O minus on this side. So I'm just going to remove the highlighting now so that I can see what I'm doing next. Now we want to show curly arrows and lone pairs to show the product formation. So what happens now is the double bond reforms using a lone pair on the oxygen. The chlorine is kicked out as a chloride ion, and it's deprotonated, so we're eliminating H and Cl from our structures to form an ester. So that's our first part of the question. Figure 4 shows an intermediate formed in the first step of a reaction mechanism of methylbenzene. So let's draw methylbenzene. So that's methylbenzene. How would we be able to make it look like this intermediate? Well, we can see that it involves an NO2, and electrophilic substitution uses an electrophile, which is positive. We can also tell that by the balancing of the charge. So we're going to use the pi bond to attack the N with the positive charge. That's going to form our intermediate. And then on the intermediate, we're going to reform the pi bond by loss of the proton. This was electrophilic substitution. Figure 5 shows the reactant species involved in the first step of a mechanism. Complete Figure 5 to show the structure of the intermediate formed with curly arrows involved in its formation. So the hydride ion is going to attack the carbonyl carbon, the delta plus carbon, and open up the double bond because the pi bond is weaker than any of the sigma single bonds. And we end up with an O minus. And this is the first step of the nucleophilic addition mechanism, because we've used an electron pair donor, the hydride ion, and we've added it, so a nucleophilic addition. We're not going to eliminate anything here. We're going to end up forming an alcohol by adding on a hydrogen ion to the O minus in the next step.